All right, so welcome for our second talk today by Alex Rodriguez, and he will talk about circle homeomorphisms and their relation to conformal welding. So please.
Hi. So I'm a PhD student at Stony Brook University, and my advisor is Chris Bishop. And yeah, today I will present a result that I posted on Archive on January. So let me start by telling you what do I mean by conformal welding. So if you take mainland US and you forget about many things, and you probably ignore some part up here, then what you get is a Jordan curve. So this is a Jordan curve. And you know that by the Riemann mapping theorem, then you can map inside and outside of the unit disk to inside and outside of the curve by conformal maps. And then you know by Carathéodory's theorem that both of these conformal maps extend as homeomorphisms to the boundary. And this gives you an orientation-preserving circle homeomorphism. Yeah. And this homomorphism is what we call conformal welding. And basically, this homomorphism follows conformal maps in this way. So if you have an arc here, you map it forward into the boundary of your Jordan domain, and then you go back by the inverse of your conformal map. Yeah. So just to show you the graph of this function, what this looks like if we plot the argument. So this is something that Chris, my advisor, has helped me putting together. And you get this when you draw the conformal welding of the United States. And let me show you how he did it, but instead of doing it for the US, I'll show you for California, since the server in which the Quasiworld seminar is based is from UCLA. So this is what you get when you draw it for California. And this was done by Chris and using Toby Driscoll's code, implementing conformal maps and how to compute them. Yeah. Okay, so as I said, every such circle homeomorphism is called a conformal welding.
So sorry, a quick question about the pictures. So I mean, you have this part where
Yes.
steep slope, right? So how do you get the steep slope? What are
This steep slope? Well, this steep slope happens in a place in which the derivative needs to be very large. Yeah. So the way in which Chris drew this picture is by taking an equidistributed grid and then pulling it back via this conformal mapping code. And at some point, the points that he had to interpolate from were like very far apart, and that led to like a big slope.
Okay.
Yeah. No, please, any questions that you have, ask me. I'm planning to go slightly under time so that there is time for as many questions as needed. So every such circle homeomorphism is called a conformal welding. And now, given that we have a circle homomorphism, the natural question is every circle homomorphism a conformal welding? So does someone know the answer?
Well, the answer, of course, is no.
Oh, of course, yeah, the answer is no. And I will show you later an example. And if we have time and if you want, I can prove to you that the example that I will give you is not a conformal welding. And then I have spoiled it already in my title, but what I prove is that even though not every circle homomorphism is a welding, every circle homomorphism is a composition of two conformal weldings. So if you give me any circle homomorphism, I can produce you two conformal weldings so that their composition is this circle homomorphism that you have given me. So this is the main theorem, and we will prove it today later in the talk. Okay, so let me start by giving you some positive results and something that is like very classical and well known, which is sufficient conditions for a map to be a welding. And the classical example are quasi-symmetric maps. And I will just remind that circle homeomorphism is quasi-symmetric if there is some m greater than 1 and less than infinity. So that if you take a pair of adjacent arcs of equal length, then when you compare in the image the ratio between their lengths, they stay uniformly bounded. So this ratio stays between m minus 1 and m. And it's a very classical theorem from the 60s by Pfluger, which says that every quasi-symmetric map is a conformal welding, meaning that there is a curve, which in this case happens to be a quasi-circle, and conformal maps, so that when you do the previous operation, you get this circle homomorphism. Yeah. And here I present the non-example. So I'm slightly cheating here because instead of writing this in the unit circle, I'm writing it in the real line, but you can go from one to the other by just using a conformal map that sends you the real line to the unit circle. And the example is the following. There is a mismatch in the powers. So when x is less or equal than 0, you have x. And when x is greater or equal than 0, you have x cubed. This example, I think it was first given by Oikawa in a paper from the 60s. And if you want, as I said later, I can show you why this is not a conformal welding. Yeah. Are there any questions? Okay. Okay. So let me just say that conformal welding is important in many different areas. For instance, it lies at the construction of like Teichmuller space. It's also very important in Kleinian groups, since there is this very stable uniformization theorem for Kleinian groups, and conformal welding lies at the very construction, like when you construct, like when you prove this theorem. It's also very important in complex dynamics, and it also appears in other contexts, like random geometry, when you glue two Liouville quantum gravity disks, and then you can see that you get SLE in some cases. And then it's also important in computer vision, and this was used by David Mumford, and I think also Sharon. So, and what I mean to say by this slide is that this theorem already gives you a lot of math. So there has been a lot going on just by just following this classical fact. There is a lot that follows from it. But in this talk, at some point, I will need to present a slightly wider class of conformal weldings, since, as you might know, the composition of two quasi-symmetric maps is again quasi-symmetric. So my theorem cannot work with only quasi-symmetric maps. Okay, and to do that, let me first start by talking about the regularity of the welding. And to do so, we will need to talk about harmonic measure, which is the heating distribution of Brownian motion. Yeah? So this means that you take a random path starting at some point, and you find the probability that it hits the boundary on a certain place. And yeah, so here we would have an arc on the boundary, and we would measure the probability that the Brownian motion that we throw from some point z first hits this set E. And the magic thing about Brownian motion is that it's conformal invariant. And what this means is the following. Yeah, so here I repeat the same. And then, yes, since Brownian motion is conformal invariant, normalized arc length on the unit circle maps to harmonic measure on the given domain that you take. So for instance, if we check what this means in terms of the of a welding map, it's the following. So if you take a set E on the boundary, and you map it back by F, so this interval I is the pre-image under F of E. Yeah, and you do the same for G. Then what you can see is that they correspond to each other via your circle homomorphism H. And now, by conformal invariance of Brownian motion, the length of this interval is the harmonic measure with base point chi, which is the one that it's mapped to by infinity, of the set E with respect to the domain, the complement of this Jordan curve that is a component that is unbounded. And the length of this interval is the harmonic measure with respect to base point Z of this set E with respect to this Jordan domain omega. So here this is omega and this is omega. Should have written a star. Yeah. And well, I mean, you know that harmonic measure is a harmonic function, so the base point does not really matter since by Harnack's inequality they will be comparable. So we just simply write h of I divided by I as the quotient between harmonic measure from outside and inside without regarding the specific base point. Yeah. And once we have this characterization, there are several ways to understand how regular the conformal welding homeomorphism will be in terms of how different harmonic measures are from inside and outside on our given Jordan curve. The first theorem that many of you will know is this theorem from more than 100 years ago that the Rees brothers proved, which says that if your Jordan domain omega is if the Jordan curve is rectifiable, then the harmonic measure of a set is zero if and only if it has zero length. And this shows that in this case, when you have rectifiable boundary, then a harmonic measure from inside and outside are absolutely continuous with respect to each other. And this means that the circle homeomorphism that you get is absolutely continuous with respect to Lebesgue measure. Yeah. Another result in this direction was proved by Nick Makarov, and where he showed that if your boundary is like if your Jordan curve is fractal, then harmonic measure gives full measure to a set of zero length. And then slightly later, Chris, together with Carleson, Garnett, and Peter Jones, they proved that harmonic measure from inside and outside are mutually singular, even only if the set of tangent points has zero length. So I know that many of you will know this, but you'll just write that this is Bishop, Carleson, John Garnett, and Peter Jones. Yeah. Okay. So for instance, if you take your favorite fractal set, which in my case it's the Bangkok snowflake, then tangents have zero length. Therefore, harmonic measure from inside and outside are mutually singular, and this gives you a singular welding by this description of the welding map. Yeah. Okay. Okay. So as I said, let's see what happens with the snowflake, and I'll remind you what the snowflake is. So you take an equilateral triangle of let's say each one of these sides has length 1, and then you add a triangle that is that has side 1/3 of the previous side, and you keep iterating this procedure. Yes, and I have not drawn what you get in the limit, but what I have here again, thanks to Chris helping me generating this image, is what's the conformal welding of the snowflake, and it looks like this. Yeah. And you might know that the snowflake is a quasi-circle since it satisfies the bounded turning condition that Alfors proved. Yeah. Are there any questions? I hope everyone can hear me.
Yeah, we can hear you.
Okay. Okay. So now the goal is to, so I have explained a bit of kind of like the general theory of conformal welding. And the goal is now to kind of like turn more into my theorem and how to prove it. And the goal at the end will be to for me to like give you a sketch of the proof of my theorem by highlighting the main points. And to do that, I need to talk about logarithmic capacity because this will be the deciding factor and and one of the main objects that we will need to study. So let me define logarithmic capacity. So suppose that you have a finite compactly supported measure on the plane, and then we define the logarithmic potential in this way. Well, we define it in this way as long as our measure has what it's called finite energy, where the energy integral is this double integral here. And given a compact set of the plane, we define the Robin constant of the compact set as the infimum of the energy of all possible probability measures that we can put on our compact set. And then once we have done that, we define the logarithmic capacity as the exponential of minus the Robin constant. I will just emphasize that once you go to higher dimensions, the definition is slightly different. And instead of having, so the logarithm is the fundamental solution of the Laplacian. And when you go to higher dimensions, this changes. And the magic that it has is that in higher dimensions, it's always positive, whereas here it can take negative values. And this is a problem that we will need to sort out later. But there is another way to define logarithmic capacity, which is the one given in this book by Carleson, that is called Selected Problems on Exceptional Sets. Yeah. But all of what I'm saying here can be found in John Garnett's book with Donald Marshall. Okay, so let's see some easy properties that are satisfied just from the definition. If some compact set has a finite Robin constant, then it has positive capacity. And you can check, for instance, that if you take a point, then a point has zero capacity, and it has infinite Robin constant. And then the other property is that if some compact set is contained in another one, then every probability measure here is also a probability measure here. Therefore, since we're taking an infimum, the Robin capacity of K1 is greater or equal than the Robin capacity of K2. And this means that the capacity of K1 is less or equal than the capacity of K2. Okay? And we extend this to Borel sets, and if we wanted, we could even extend it to analytic sets by taking the supremum of capacities of compact sets that are contained in our Borel set. Yeah. Okay. So let me show you a couple of examples that will be very important for us of capacity of like some known sets. Capacity can be a very difficult object to compute. It is as difficult as find a suitable conformal map, or I mean, more precisely, you need to find the right Green's function on your on a certain domain if it exists. And for instance, the capacity of a circle is its radius, and the capacity of a line segment between 2 points AB is the distance between them divided by 4. Yeah? And this we will use a lot when I prove the main result of my paper. Okay. So then another important property of capacity is that if capacity is 0, then our set E has Hausdorff dimension 0. And we can see this straight away from the definition. If it had positive Hausdorff dimension, then we would have a Frostman's measure, and we could check that it would need to have finite energy. So what I'm trying to say by this is that capacity 0 sets are really very small sets, like they're tiny sets. As I said, points have capacity 0, and you can see that capacity once you restrict it properly, is subadditive. So, for instance, countable sets also have capacity 0. Hmm? Okay. Okay, so this is just what I wrote before in case someone didn't remember the definition of logarithmic capacity. And now what I want to emphasize is that well-behaved circle homeomorphisms preserve capacity 0 sets. And the classical example of maps that preserve capacity 0 sets are biholder maps. And we say that the map is biholder if there is a constant that is less than infinity and some positive exponent, so that this inequality holds. And whenever that happens, we can see from the definition again that the capacity of a set will be 0 if and only if the capacity of the image will be 0. And this is not explicitly stated in John Garnett's and Donald Marshall's book, but it can be proved from what they have. Yeah. Okay, and I will emphasize that quasi-symmetric maps are bipolar. So quasi-symmetric maps will preserve capacity 0 sets. And now, after doing this detour through logarithmic capacity, I want to turn even more into my theorem, and I ask the following: how do we prove that every circle homomorphism is a composition of two conformal welding homomorphisms? And the tool appeared in 2007, and it was and they were these log singular homomorphisms that Chris introduced. And we say that the circle homomorphism is log singular if there is a Borel subset of so that it has capacity 0, and so that the complement maps to a set of capacity 0. Yeah. Yes. Here I draw what a log singular map looks like. So you can see that it basically needs to take very small intervals to very large intervals and alter this. And the nice and fantastic theorem that Chris proved in 2007 is that every log singular homomorphism is a conformal welding. And this was great because the theorems that came before Chris's result were showing that if a circle homomorphism is regular enough, then it is a conformal welding. And he proved that if you choose the worst circle homomorphism that you would ever want to consider, then it's also conformal welding. And as we have seen before, there are many examples in between that are not conformal weldings. So these homomorphisms are very singular. And as I said, a quasi-symmetric map will never be log singular, for example, since it will preserve capacity 0 sets. Okay, so if we want to use Chris's result to prove this theorem, then this theorem amounts to the following, which is that every circle homomorphism is a composition of two log singular maps. And equivalent, we can write it in the following way. We could also prove that for every circle homomorphism, there is a log singular circle homomorphism, so that this composition is also log singular. Okay? And this is actually the version that I will show to you today. Okay. Okay. So as I said, this is our target. And before I really get to the proof, I want to take like a few minutes to settle some sort of question that was sorted out a long time ago, but we somehow forgot, which is whether or not the composition of two conformal weldings is a welding again. And I will recall the non-example that I showed before, which is x on the negative real numbers and x cubed on the positive real numbers. And what I will observe is, well, what I will recall is the previous lemma that I mentioned, which says that if we have a biholder map, then a set has capacity 0 if and only if the image also has capacity 0. And what this implies is that if we take any log singular circle homomorphism, then our circle homeomorphism composed with the inverse of this log singular map will also be log singular. Yeah. Yes. And this follows by taking this set here, which so that the complementary is mapped to a capacity zero set, and capacity zero set is preserved under our Byholder mapping. And this proves that weldings are not closed under composition, which was initially showed by Bainio in his PhD thesis in 1985. And another example was recently given by McMullen. I will say that my example, Bainio's example, and McMullen example are similar in the following sense. We all show that for a certain couple of maps, they compose to a mapping of this form. But the great thing is the following. Bainio found an explicit pair of maps that do that. And same did McMullen. But he did it coming from like some dynamical point of view. His paper was recently it's a recent preprint, so it's a very nice paper. And as I mentioned, I just gave you an argument of why weldings are not closed under composition by using Fries's theorem. Okay. So now let me go back to my theorem and now for real. And the key tool that I introduced in my paper are called log singular sets. And log singular sets are the sets so that there is a log singular homeomorphism so that this condition holds. So E is a log singular set if it has capacity zero, and there is a log singular homeomorphism so that the complement goes to capacity zero under this homeomorphism. Yeah. And let me just give you let me just make a quick remark, which is that log singular sets cannot be closed. And that is because if they were closed, then the complement is open, and the image of an interval is always an interval under a circle map, so they would have positive capacity. And the goal is now to construct a lot of log singular sets, many of them. So yes, so we want to quantify them, and the question is how. And to do that, what I did was introduce what I call addresses. And to think about addresses, you can think about the dyadic partitions. So which are these partitions. And then you can also think it from a symbolic dynamics point of view. So let me explain you what is an address by kind of like using first a picture, and then I'll give you a definition and the properties that I need the partition to satisfy. So if you give me an interval or an arc, then what I can do is decompose it into like a certain number of intervals or arcs, so that they have disjoint interiors and they add up together with the closures to the whole thing. And then I keep iterating this procedure. So, and then you keep going farther and farther. And I call the address of this interval these numbers here, which is telling you in your partition what order are you following in each step. Okay? So for instance here, if we wanted to go to this interval, then we will need to choose first the first one, the second one that appeared. Then we would go to the fourth one, and then we would go to the first one that appears. Yeah. Okay, and now let me give you the actual definition. So if you have a word of length n, where each one of these entries is a natural number, then we suppose that we have some associated intervals to this collection of words that they satisfy the following. If we have two words of the same length, that they are different, then the corresponding intervals have disjoint interiors. If n is less or equal than n, and a word of length n is contained in a word of length m, then am, I think that here I probably wrote here I wrote this in the other way around. This should go in this direction. Then we can obtain the word am by adding a few entries to the word an. Yeah? Where these are the entries of the word an. And the last condition is that given a word an minus 1, then the corresponding interval that we get is the union of all the subintervals that start by these n minus 1 characters. And we call an the address of this interval because we can recover this interval by taking this intersection. And this is what I depicted here for this interval. And the key tool is to use this interval, these decompositions to build log singular maps. And this is what I do in this lemma. So it says the following. If you have a partition of a certain subarc, and then you have another partition of a certain subarc, what I want to do is build a log singular map that goes from one to the other. And the conditions that are needed are the following. So suppose that the length of the intervals decrease, and this will be needed when this is needed in the proof when we prove that the maps that we will get are continuous. If this set and this set both have capacity 0, then we can find a log singular homeomorphism so that the image of the complement of the first one is the second one. And since this formula is long, let me explain you what it basically says. So here, what we are doing is going only over the odd elements of our partition. So we have a partition given by a bunch of elements, and we're only looking at the ones that have like a odd entries. So we would be taking this one and this one. And what we ask is that this set has, like this set that we would obtain at some step n, has very small capacity. So small that when we take, that when we make all of these operations, then we get a set of capacity 0. And then on the other side, we take the even number ones. So we would get this one, but with j's, we would get this one and this one. And we ask the same for these sets. Yeah. And then my claim is that there is a log singular map between these two sets, or in other words, both of them are log singular sets as I defined before. And the proof is a picture. So you have two partitions, and you want to match them up. And there is something that I didn't say, but it was here in the lemma, which is that at step n, which would be when we consider words of length n, then all the words that appear have exactly the same length. They have the range of from which the numbers can range on our words is the same. Okay, and what we do is basically send one to one and to the other by a linear map. So these maps, I will be taking them to be linear in each one of them. Yes. And if we do that iteratively, what we get in the limit is a continuous map because we have asked this condition. This is also an homeomorphism because if we have 2 points So if we have 2 points that are distance epsilon apart, then for some epsilon small enough, there will be in 2 intervals that are disjoint, and once we go to the limit, then they will also be different. So via this, via the limiting mapping, they will be mapped to different things, and this proves that the limiting map is a homeomorphism. So this is step 1, which is saying what sets can be log singular sets, and producing the log singular map between them. Yeah. And let me go back to my theorem, which is that for every circular homeomorphism, there is a log singular map, so that this mapping here is log singular. And what I say is the following. So what I'm doing now is revisiting what helped us before when we were proving that the composite. So if we need to decompose a bifolder map, then we can do so by taking any log singular map. And if we want to emulate what works there, what we would like is to find a log singular set E, and a log singular map associated to it, so that the image under our given homeomorphism of this set also has capacity 0. Okay? Because if this happens, then our mapping is log singular, and this is very easy because this is very easy to check, because if you take this as your capacity 0 set, then if you take this set and you map it forward via h-1, then you get E. And if now you map it forward by phi, this has capacity 0. Yeah. So this map under those conditions would be log singular with this log singular set. With this log singular set here. And that's our goal. Our goal is to see that given any circular homeomorphism, we can always find log singular set that satisfies this. And this is the second part. And this is the last part of the theorem, and that's what I want to explain now. And the proof is basically a picture, because suppose the following: suppose that you have a partition of the unit circle that satisfies these conditions, this condition here, and so that at step n, all elements become very small. Yeah. Then what you can do is map it forward via your homeomorphism. But in general, since your homeomorphism can be bad, very bad, then you will get some intervals that will increase a lot their length. So if you take a random log singular set and you map it forward, you will not get in general log singular set. But for this special case, what we can always do is the following. So here, as I said, in general, these intervals will not be small enough, but what you can always do is just make them small enough, as small as needed. And so you make them as small, so the condition here in this lemma is satisfied. And then once you have done that, then you just go back and you get a certain subinterval. Since these intervals satisfy the condition, the log singular condition, then these subintervals will also satisfy this condition. And from the way you have constructed them, these intervals will also satisfy this condition. So you will be in the hypothesis of this lemma, and you will get, so sorry, what I want is that the image is like very small. So if you apply this lemma to these intervals, you will get this mapping H. Yeah. And what you know is that if you map them forward via your mapping fee, then they will also have capacity zero. And that completes the proof of this result. And therefore, it completes the proof of this theorem. And by using Chris's result, which shows that log singular homeomorphisms are conformal weldings, we conclude that every circle homeomorphism is a composition of two conformal weldings. Okay? Yeah, so I don't know if I have gone very fast, but let me, so this was the last kind of like math slide that I have. And let me explain some open problems that are related with this. So these log singular circle homeomorphisms are associated with some curves that are called flexible. And one very interesting problem would be to characterize alpha singular curves in the sense that it would be ideal to know what are the curves that yield circle homeomorphisms that are singular with respect to some Hausdorff measure. The next question, which we still don't know, is how bad can a curve with biholder welding be? That we don't know. We don't know yet. And then in this direction, and this would be great, because I think it would have a lot of applications. It would also be very interesting to know if the composition of two biholder weldings is also welding. And then, I mean, right now there is not a real and very big hope to understand the set of weldings. But one thing that we can ask is if the set of weldings is Borel. And to see more about this question, you can see Chris's a preprint conformal removability is hard. So by Chris. Okay. And there are some other problems that would be, in my opinion, very interesting. So, for instance, in my theorem, which is that every circle homeomorphism is a composition of two conformal weldings, I need to use very badly behaved weldings. I need to take log singular weldings, which are very badly behaved circle homeomorphisms. And the question is this necessary? Like, can I get the same result with kind of like a better behaved class of maps? And if not, how could I do that for biholder circle homeomorphisms? Or is the composition of two biholder weldings or weldings? So these are some set of questions that are related with what I talked about today. And yeah, I think I finished a bit early, but I guess it's better to finish early than late. Thank you all for your attention.
Yeah, thanks a lot. So let's thank Alex for a very interesting talk. So are there comments or questions?
Maybe just a very naive question about one of the last things you said. You said you would like to know whether you can replace your not so nice weldings that you used to build your theorem by nicer ones. Do you know any constraints, like you cannot get nicer than a certain thing, like you know that you cannot restrict to an overly nice class of maps?
The truth is that the main obstruction is that we don't really understand weldings. Given a map, it's very difficult to tell whether or not it is a welding. So I don't really know. I mean, the first thing that I would personally do, is check whether or not every log singular homeomorphism can be written as a composition of biholder weldings.
Okay.
Which is not true, actually. So not even that, because biholder bicolor weldings, bicolor maps preserve capacity zero sets. So the thing is that there is a big gap between what we know, what are nice weldings, nicely behaved weldings, and these kind of like awfully behaved weldings. So it's and in my result, I rely completely on these log singular maps. Without them, I don't know. What I do know is that the maps that Kurt McMullen and Bainio found are not log singular. So McMullen, I think, uses the question mark function to produce it. At least that's I'm pretty sure that that's what he uses. And then Bainio just uses a logarithm, a map that looks like a logarithm and a map that looks like an exponential, but twisted. And then they compose to the corresponding maps. So we know that the theorem that, so a consequence of the theorem that I proved, which is that weldings are not closed under composition, are can be checked by mappings that are much better. So yeah, I don't know. My guess is that if you lower the regularity, if you increase the regularity of your circle homomorphism and you take them to be, for example, bipolar, then the answer should be better. But I don't know how better. I don't know.
Okay. You mean the composition property should be better?
Yeah.
Yes. Okay.
Yes. Once you restrict a bit the mappings that you consider.
I guess the basic problem that you mentioned, right, is that beyond quasi-symmetric maps, we have no kind of general class of weldings, right, that is, well, let's say, reasonably well behaved, right? I think that's the basic.
Yes. I mean, there is an equivalent definition of welding that involves being able to solve a certain PDE, which is some sort of degenerate Beltrami equation. But that condition is very difficult to check. It's very easy to check for that it's satisfied for quasi-symmetric maps, but we don't know. Yeah. For instance, we don't even know what are the weldings that arise from images under the bitmaps of circles. We have no idea. There is no good characterization. So if you allow cusps, then we don't know we don't know a nice characterization of like the weldings that arise. In the same way that we know that for quasi-circles they need to be quasi-symmetric maps. So yeah, there is a lot of work to be done. That's one of the takeout of this story.
Yeah, I mean, one of my favorite problems is always, I mean, you mentioned these probabilistic models, right? And these curves that you get, they are typically not quasi-circles or quasi-arcs, right? But they're not far from quasi-arcs. So one could speculate, is there just somehow a small extension of the class of quasi-symmetric maps that somehow would take care of curves that arise from these models? I think that would be a very interesting, probably very hard question to study.
Yes. So let me give a reference related with this question, because some similar approach was done, I think, in 2010. And this is a great paper by, so the paper is called Random Conformal Welding. And I hope I don't miss anyone. So this is Astala, Klipianen, Jones, and Eero Saxon. And here they do precisely what you just mentioned, Mario. They see that if you don't deviate too much from, what they see is that if you have, so in some way when you have quasi-symmetric maps, what you have is regularity at all scales, right? That's the definition of quasi-symmetry. And what they check in their paper is that if you have regularity at most scales in some way, then you are also welding. And they quantify this in some sort of random way.
Yeah, I mean, they use a condition that is due to Lechto that is maybe not so well known, that is actually very...
Exactly, yeah.
Tim, you had a question, but
here.
I think, Tim, you had a question, but I think this was exactly the same question that I just mentioned. Tim?
Yeah, I think so. Yeah, I was going to ask if there's a rougher class than quasi symmetry that is weldings that's known to be close under composition, but Mario, you seem to answer that negatively.
Well, I mean...
Yeah, I think it would be very... I'm sorry.
Yeah, closed under composition is, of course, it's an additional burden. If there's just a slightly larger class that is somehow well behaved, I mean, this would already be quite interesting, I think.
Yes, I think so too, and I agree with you that the direction is in terms of these mappings. So it would need to be checked if when you take their mappings, then if you take the composition of two things that behave nicely at all scales, then if the composition also behaves nicely at all scales. Since I prepared the slides just in case, and you just mentioned this Lecto condition, and I think it would be great to advertise it, I can write it for you. And the condition is somewhere down here. Okay. So if you give me permission, I can explain it. But
yeah, please go ahead.
Okay, so the thing is the following. This is an equivalent condition for being a welding in terms of the solution of a PDE. And the PDE is the following. If you have a circle homeomorphism, P, then you can consider the Berlin-Alfors map, which is a self-map of the unit disk. That is a C1 orientation preserving homeomorphism. That it follows that is also quasi-conformal on each compact set, and that it has boundary values phi to the -1. So this map to the -1. So this mapping always exists. Yes? And therefore, you can define a Beltrami coefficient in the following way. In each compact set, you take the usual one. Because this map is quasi-conformal, so it's well-defined. And then outside of the unit disk, you take 0. And if there is a global homeomorphism that has this dilatation given by this map, then your mapping is a welding. And the image under this map of the unit circle is the Jordan curve that this welding arises from. And if you have read the proof that every quasi-symmetric map is a welding, this is what you have. But in that case, then the Alfors-Berling map actually gives you a quasi-conformal map of the entire disk. So this Beltrami coefficient is uniformly bounded. And therefore, you can use this fantastic tool, the measurable Riemann mapping theorem, to obtain a global homeomorphism. So the measurable Riemann mapping theorem guarantees the existence of this homeomorphism. And I claim that then this is a welding. And the proof is short. Outside of the unit disk, the dilatation is 0. Therefore, your mapping is conformal. So this is already what you want. And then inside of the unit disk, well, this map that you have obtained, if you can obtain it, it has the same dilatation as this map. So if you compose them in this way, they will cancel out. So the mapping inside will also be conformal. And you can check that then the boundary values are precisely what you want. Yeah. So this here should be pi. But yeah, when you do that, what you have is a welding. If you can do this process, and this as an example gives you that quasi-symmetric circle homeomorphisms are conformal weldings, and this is the PDE that you need to solve. And what Mario mentioned is that Pauli Lecto gave a condition for when this PDE has a solution. And this is in some proceedings of the Scandinavian Congress for Mathematicians from the 60s, I think. Yeah, I think it's from 1960. But yeah, it's a very nice paper, and it explains this condition under which you can solve this PDE.
Yeah, okay. Yeah, this is definitely a condition that should be better known. Yeah, do we have any more questions or comments?
I have one question, simple one.
Go ahead.
Hi.
You had the example of x and x to the third, and that was not a welding. Can you do
Yes.
instead of 3, 1 plus alpha?
Yes, exactly.
Okay.
What happens is that, so this is why the argument that, so the first person that proved that was Kotaro Oikawa in 1960, I think. I have said 1960 a lot of times, so I don't know if half of them I have been wrong. But Oikawa proved that if you have a map that has a mismatch in the powers, then it's not a welding. Yeah, and the way in which he proves it is by constructing some path families that so that if it was a welding, they would need to kind of have the same modulus, but you can check that under those conditions, one has 0 modulus and the other one has positive modulus, which is not possible if your mapping was a welding. But yeah, any mismatch in the powers gives you something that is not a welding. Yeah.
Great. Thank you.